Hello, everyone, and welcome to the 5th session of the massive open online course for the University of Nicosia. Very excited to be chatting with you again. And we're running 1 hour different because of the change in daylight savings in the United States. I hope you all got that message. Let's get started. First of all, can everybody hear me okay in the channel? Can you hear me? Can you see me? Audio good, great. First question comes from Rohit. If we are making 2 different blocks, transaction and witness block, do we still have the same size on the blockchain, but just 2 different blocks? Please elaborate on segregated witness. Rohit, no, there's no 2 different blocks. The transaction data and the witness data are part of the same one block that has both of those data sets in it and has 2 Merkle trees, which are committed in the Coinbase transaction and the transaction Merkle root in the header of the block. So the witness section and the transaction section are in the same block, but they're not mixed together, meaning the witness part is not inside each of the transactions, but it is in a separate part of the data structure, and it has its own Merkle tree. That means that if the witness changes, for example, because of transaction malleability, it doesn't change the transaction ID, and it doesn't change the transaction Merkle root. Rohit, in light data payment security, does this channel have the same security and authentication operations like the blockchain? Yes. So it's really important to understand that a transaction on Lightning Network, if you're doing a Bitcoin channel, is a Bitcoin transaction. Now, imagine if I created a transaction and instead of broadcasting it on the Bitcoin blockchain, I signed the transaction and then gave it to you. And you can broadcast it whenever you want, or you can just hold on to it. Anytime you take that signed transaction and broadcast it, you get the outcome of that transaction. So we've exchanged the signed transaction, we just haven't broadcasted. That's how Lightning works. So Lightning payment channels are parties exchanging signed Bitcoin transactions, and it has the exact same security and authentication and authorization qualities, the same security guarantees as the Bitcoin blockchain. In fact, that's why Lightning works, because it requires the security of the underlying Bitcoin blockchain. Lightning is routing smart contracts, pre-signed Bitcoin transactions, and it needs those smart contracts, those pre-signed Bitcoin transactions, to be secure, to be valid on the underlying blockchain. Ricardo asks, wouldn't it be a better solution to raise the block size limit like Bitcoin Cash did, rather than use segregated witness, which will add more data between 38 and 47 bytes in the Coinbase transactions? Well, Ricardo, the solution that is created by segregated witness isn't just about scaling. So while raising the block size limit like Bitcoin Cash did, more on each block and therefore attempts to solve the scaling issue in a different way. It doesn't fix transaction malleability, which was really the primary reason for segregated witness. Segregated witness is first and foremost a transaction malleability fix, and secondarily a scaling fix. So Bitcoin Cash's increase of the block size limit hasn't solved transaction malleability, which means that you can't build complicated and sophisticated smart contracts on top of Bitcoin Cash because those are not secure because of transaction malleability. So you can't do things like payment channels that are open-ended and persist forever. The current implementation of Lightning Network, for example, it can't run. Now, Bitcoin Cash has a plan to fix transaction malleability as well. So on the Bitcoin Cash side, they decided to fix scalability first and transaction malleability second. The segregated witness approach was an approach that fixed transaction malleability first, did a bit of scaling, and anticipates a future block size increase and change in the block header format as part of a hard fork for more scalability increases in the future. So it was simply a difference in the order in which things have been done. Whether it's a better solution or not, that's really up to you to decide. You get to choose. If you think that what Bitcoin Cash did was a better solution, then you can use Bitcoin Cash. If you think that what Bitcoin did with segregated witness is a better solution, then you can use Bitcoin. In fact, you can use both. You can use both Bitcoin Cash and Bitcoin, and Ethereum and Litecoin, and Monero and Zcash, and all of the other systems. And even better, because of the Lightning Network, we'll soon be seeing the possibility of routing payments across all of these blockchains simultaneously so that you can send the payment in Bitcoin and it can arrive at the other end in Litecoin or Ethereum or something like that. This is about choice. You have the choice to use whatever you think is the best approach to scaling. Jesse asks, SegWit security, are there any concerns about the potential increase in the number of invalid blocks propagated if not enough people are storing the unhashed signature data on their nodes? So what Jesse's talking about is the idea that if people decide to not store the witness part and only store the transaction part, is there a potential increase in the number of invalid blocks propagated? Not really, because ultimately, both the miners and those who are validating witness data ensure that invalid blocks won't get propagated very far because they will be orphaned. And don't forget that there is the mining reward incentive to keep miners honest. They have to validate witness data. Otherwise, if they produce invalid blocks, those invalid blocks will be rejected by the majority of the network. Jesse asks a follow-up. If I'm not storing signature data on my node, is there a chance that I could not verify the occurrence of a previous transaction? If that is the case, should large transactions remain off SegWit or the Lightning Network, insofar as you're not personally storing signature data? No. Jesse, signature data is part of block and transaction validation, whether you choose to store it or not. Keep in mind that as Bitcoin works today, most nodes validate signature data only once, and then they stop validating it and don't necessarily have to store it in the future. If you decide to have a node that is not validating witness data or have a node that is not storing witness data, those are two very different things. In fact, you can't configure your node to not validate witness data. You can only configure your node to not store witness data. What does that mean? That means that when you receive a transaction, you will validate the witness data. You may choose not to store it on your blockchain long-term. And in fact, you don't need to store it once you validated it. If you choose not to validate witness data, you are not running a validating node. And if you're not running a validating node, you are essentially operating in simple payment verification, SPV mode, which means that you are relying on the miners to do the validation for you. That is not an authoritative validation. So you have a range of choices. You can validate but not store. But if you choose not to validate, then you might as well simply run a light client because you are no longer validating transaction data. You're running an SPV node. And you've always had the opportunity to run an SPV node. And an SPV node has less security than a fully validating node. The only difference now is that you can be a fully validating node, but not fully store all of the data. Just like you can prune the blockchain to reduce its disk space, you can also not store witnesses. Let's check in with the chat room, see if that's making sense, and if there are any follow-up questions. Very good. Most of the chat room has gone off on a tangent and is talking about something else, but we'll continue. Very good. Stephen asks, oh, sorry, I almost skipped one. Simon asks, how is the witness part included in add-on blocks and verified in the Coinbase transaction? So Simon, at the moment, or since the beginning, every single transaction is hashed to produce a transaction identifier or transaction hash. That transaction hash is put into the bottom of the Merkle tree, and all of the transactions together create a Merkle tree, and the Merkle root of that tree, which is one hash that summarizes the entire tree, is stored in the header of the block. The witness parts are also stored in exactly the same way, just in a different tree. So every single witness from every single transaction is put into the bottom of a Merkle tree. The Merkle tree summarizes all of those things into a Merkle root, and this one's called the witness Merkle root. And the witness Merkle root is incorporated in the Coinbase transaction. Validation of the block requires validating that the Merkle root of transactions is correct and includes all transactions, and the Merkle root of witnesses is correct in the Coinbase and includes all witnesses, and validating, of course, every witness against every transaction. So validation hasn't changed at all. Simon asks a follow-up question. How would the bigger blocks of 1 to 2 megabytes in SegWit 2x have been accepted by nodes and miners? Would I need to change the parameters in my Bitcoin Core configuration file? So just to clarify, what Simon is talking about, SegWit 2x, was a proposal that was not implemented, that was planned for an increase in the block size as well as an implementation of segregated witness at the same time. SegWit 2x never happened. Instead, Bitcoin Cash implemented a block size increase, and Bitcoin implemented SegWit without a block size increase. Instead, SegWit increased the capacity of the block to up to 1.7 megabytes, I believe, is the maximum. So how would the bigger blocks in SegWit 2x have been accepted by nodes and miners? SegWit 2x would have been a hard fork. You would have needed to implement new consensus rules with a new version of software that implemented that hard fork and remain on the majority consensus of the network. But SegWit 2x didn't happen. And part of the reason it didn't happen is because there wasn't enough agreement to get the majority consensus. Stephen asks, how will the Lightning Network handle distributed denial of service attacks? Well, Stephen, that really depends on what kind of distributed denial of service attacks we're talking about. In order to create a Lightning Network payment channel, you have to commit funds. And that makes it difficult for someone to simply create payment channels and not use those payment channels. Secondly, in order to propagate payments across payment channels, there usually is a small fee. And we'll see how that plays out and whether that will lead to distributed denial of service attacks. Also, Lightning Network nodes, just like Bitcoin nodes, monitor the type of information they're receiving from adjacent nodes from their peers. And if they see that the information they're receiving is incorrect or invalid, they will limit the connection or potentially even ban the nodes that are misbehaving. All peer-to-peer networks have to have some mechanism for protecting against misbehaving peers. And the most common way to do that is to either throttle or ban for a short period of time or potentially ban for a long period of time. So handle of service attacks in the same way that every peer-to-peer network handles them. And that's an ongoing process because as each type of attack is handled, attackers come up with new ways to attack the network, and that forces the network to adapt, which forces the attackers to adapt, which forces the network to adapt. And gradually you evolve the system to become more and more resilient to denial of service attacks. Bitcoin itself is under denial of service attack all the time, and it gradually evolved to become quite strong and resilient against denial of service attacks. That doesn't mean they're impossible. It just means they're not very effective. They cost a lot of money to execute, and they don't really do much. The same thing with the internet. TCP/IP, DNS, HTTP, many other protocols and infrastructures on the internet have gradually evolved to handle bigger and bigger distributed denial of service attacks and become resilient. Let me check back into the chat room, see if everybody's paying attention. A follow-up question from Susanna: who bans a node, and how does banning a node work? Well, this is a peer-to-peer decentralized network, which means that your own Lightning Network node connects to 10 or 15 other nodes and uses that to create a mesh network. So your node decides what nodes to connect to, and it decides whether it needs to ban one of its neighbors from misbehaving. So who bans nodes? Everyone bans nodes. If they start misbehaving, everyone who experienced that misbehavior will ban those nodes, and eventually they will not be able to connect to the network at all. That's how it works in Bitcoin. That's how it works in Lightning Network. There is no centralized authority here. Each node decides whether to ban its neighbors or not. Youssef asks, what type of malleability and scalability issues can Bitcoin present without using segregated witness? So that's a great question, Youssef. If you make a transaction today without using segregated witness, a third party can malleate that transaction, which means they can modify it in ways that you haven't authorized and retransmit a competing transaction that has a slightly modified signature, such that the transaction is still valid, but its transaction ID has changed. This causes a number of problems, especially since if you have other transactions that depend on it, and the transaction ID has changed before it's mined, then those other transactions are invalid, and they need to be changed too, which means you can't create unbroadcasted transactions and know that they will remain exactly you can't each of them is confirmed. The transaction ID can be changed by a third party and rebroadcast as a separate transaction. So malleability is quite a significant problem when it comes especially to smart contracts, more advanced functionality, chained transactions, and things like that. If you use transactions that do not have this today, those transactions are still susceptible to malleability. So by using segregated witness addresses and segregated witness structure in your transactions, you ensure that those transactions are not malleable. And that means that protocols that want to use smart contracts in Bitcoin or chain transactions together or create payment channels use only segregated witness transactions so as to make it impossible to malleate those. Yusuf also asked, how would you know that you are using segregated witness? Well, it depends. Your wallet may have a special function in order to use segregated witness. Keep in mind that using segregated witness has two parts. You can send to a segregated witness address, and there's two different types of segregated witness addresses. There's segregated witness addresses that are wrapped in P2SH. Those start with a 3, and they look like multi-sig addresses from the past because those are also wrapped in P2SH. Or you might see one of the new native address schemes for segregated witness, where the address you're sending to starts with BC1. If you see BC1, that's a segregated witness native address. So you know that that's segregated witness. And the reason we still have the P2SH or pay-to-script hash addresses that start with a 3 is because that's backwards compatible. It allows a wallet that doesn't yet understand the new segregated witness native addresses to still be able to send to a segregated witness wallet without having to know about it. And that would be a 3 address, which is accepted broadly by all wallets today. If your wallet is sending from a segregated witness address, then that transaction and the inputs that are from a segregated witness address will have the witness in a separate part of the transaction. You may not really see that. You will probably just know that your wallet is capable of handling segregated witness addresses. It also means that when you produce a receiving address for someone else to send you Bitcoin, then that receiving address either starts with a 3 or it starts with BC1. If it starts with BC1, you're definitely using SegWit. If it starts with a 3, you may be using SegWit, or you may be using a multi-sig address or some other script. And if it starts with a 1, traditional old-style Bitcoin, you're definitely not using a segregated address. Jamie asks, in a Lightning channel, what happens in a 3-person scenario if the third person does not send the reimbursement? Well, in any Lightning Network scenario, if one of the parties fails to finish the commitment to a channel, does not update their state, or does not close the channel when asked, then the other party can close the channel by transmitting one of the prior states. The only way that balance can be pushed forward through the channel is if the parties share a hash preimage, which is the secret for unlocking hash time-locked commitment. And in that case, the party who has sent that balance can also receive the same balance from the previous channel endpoint with the same secret. So you don't have to trust that any of the other parties participating in Lightning are going to behave as expected. In fact, the whole point of this is that you do transactions with people who are not expected to behave in any particular way. They may disappear. They may stop responding to channel requests. They may refuse to close a channel. They may refuse to forward a hash time-locked contract. They may do whatever they want to do. It doesn't matter. You don't need to trust them, because at every step of the way, you have a signed Bitcoin transaction that is valid, that allows you to recover your funds. And that's the whole point. The whole point is that the network itself does not require trust between participants. All right, I think we've covered a lot of topics on Lightning and segregated witness. I'm going to check in the channel, see if we have any follow-up questions. And if we don't, we'll go forward and start talking about forks, which is the next topic from the previous session. All right, we seem to be having some audio problems. I hope you are able to hear me now. Very good. Let me just repeat some of the information that you may have missed. You can tell if your own wallet supports segregated witness based on the addresses that your wallet gives you to receive money from others. If your receive address starts with a 1, then you do not have a segregated witness capable wallet. If your receive address starts with a 3, then you might and likely have a segregated witness capable wallet. And if your receive address starts with BC1, then you definitely have a segregated witness capable wallet. Follow-up question. Why do Lightning Network participants need to be online to execute transactions? Well, that's not entirely sure. It's not entirely true that the Lightning Network participants need to be online to execute transactions. They need to be online to start a transaction. So, for example, in order to create an invoice to be paid, they need to be online. And under some circumstances, they need to be online to monitor the channels, but they can also outsource the monitoring of channels to third parties. Keep in mind, Lightning Network is intended to be a live, small payment, fast network. It's not intended to be a batch, big transaction, long-term payments network. That is best done on-chain. Jorge asks, why is nobody making use of the malleability bug in Bitcoin or Bitcoin Cash? If you can interject a transaction, change the signatures, pay a higher fee, and broadcast it again. Jorge, you can change the signatures so that they're still valid but slightly different, but you can't change who's getting paid. You can't change the amount. You can't change where the money is coming from. So you can't steal money with transaction malleability. All you can do is confuse the system by changing the transaction ID. So there's not much point. The only reason you would use transaction malleability as an attack is for denial of service. And it makes it difficult for certain types of smart contracts. But pretty much since 2013, every single exchange and provider accounts for and knows about transaction malleability, and they don't allow you to double withdraw or cause other problems with transaction malleability. All right, let's move on to some of the questions on forks to fill in from last session. Makram asks, why is a new currency created when forks happen? Why can't we keep using the Bitcoin currency on the new protocol, even if it's a new fork? Well, the reason for that, Makram, is because when a hard fork happens, the rules have changed. And when the rules have changed, the new rules are not compatible with the old rules. That's why it's called a hard fork, which means that you can't simply move currency from one network to the other. The two networks become distinct. They have forked, and they have forked hard. They are now separate blockchains with separate rules. And so therefore, as soon as you have separate blockchains with separate rules, and the currencies are no longer interchangeable, you can't keep using the same currency, because inevitably the prices are going to diverge. Because they behave differently, they're going to be priced differently. And the rules are different. and you can't transfer one to the other without doing an exchange, which again makes it so that they are in effect different currencies. It's not that there are technical barriers to prevent you from treating it as the same currency. It's that they are economic and technical barriers. You have a divergence of the consensus rules. You have a divergence of the networks. You have a splitting of the liquidity. You have a splitting of the fungibility. And therefore, you have a splitting of the economics. Simon asks, what is the difference between a fork of the Bitcoin Core reference client and a fork of Bitcoin? That's an excellent question. In fact, we use the word fork to describe 3 or 4 different scenarios. First of all, creating a fork in software, which is a very common thing, you see it on GitHub and other software projects, means simply creating an alternative version of that project where different developers are pursuing different goals. And that doesn't necessarily change the consensus rules, the behavior on the network, or anything like that. So there are, in fact, a number of Bitcoin Core reference client forks that are entirely compatible with Bitcoin Core and operate on the same Bitcoin network and do not cause a fork of Bitcoin because they use the same consensus rules. One example of that is the KNOTS distribution, K-N-O-T-T-S, KNOTS distribution, which is a fork of Bitcoin Core by Luke Dasher. And that fork simply has some different software distribution policies, but it follows the same consensus rules as Bitcoin Core. And you will see Bitcoin KNOTS clients operating on the Bitcoin network without any problem and interoperating with Bitcoin Core. So that's a software fork. Another thing you might see is a change that causes a network fork, where the fork occurs in the network, where the network splits in two. And you can have that even without a change in the consensus rules. It can cause quite a few weird problems. And then finally, the one you're most likely thinking of is a consensus fork. And a consensus fork is a change in the consensus rules. And there's 2 types of consensus forks. A consensus fork, which is a soft fork, where the rules have become more restrictive, and therefore clients following the old rules can still follow the new rules. And a hard fork, where the rules have become less restrictive, which means that clients following the old rules will find the new rules to be invalid in certain circumstances. That's the difference between a soft and a hard fork. And those are consensus forks, which means the consensus rules have changed either in a backwards compatible or non-backwards compatible way. Simon asks as a follow-up, was Bitcoin Unlimited a separate blockchain because the nodes accepting bigger block sizes would have been banned by the nodes operating on Bitcoin Core? Yes and no. First of all, Bitcoin Unlimited was a change in the consensus rules, and the nodes accepting bigger block sizes are running different consensus rules. Now, these consensus rules are less restrictive than before. So before the change in Bitcoin Unlimited, a 1 megabyte block was acceptable. After the change, a greater than 1 megabyte block was acceptable, which is a lesser restriction. And when you have a lesser restriction, that means that nodes that are expecting a 1 megabyte block, if they see something bigger than 1 megabyte block, see that as invalid. That means that's a hard fork consensus rule change. So not only would Bitcoin Core nodes refuse to accept the blocks produced on that network as valid, but this would also, as a secondary effect, cause a network fork, where the nodes that are propagating these larger blocks will get banned, because as far as the Bitcoin Core nodes are concerned, these nodes are propagating invalid blocks. So the change in consensus rules, the hard fork in the consensus rules, then causes a split in the network, a network fork, because those nodes get banned for propagating invalid blocks. Kirill asks, how does the community come to consensus about changes in the rules, particularly soft forks? If people vote with their CPU power, does this mean that only miners who really have a say? What about developers who don't mine or are silo mining? How do they represent their view? Kirill, at first glance, it appears that miners are the only ones who have say. But that quickly falls apart once you realize that miners need to pay their electricity bills. And in order to pay their electricity bills, they need to be able to transact in the currency that they're mining. In order to transact in that currency that they're mining, they need exchanges. They need wallets. They need merchants. And in order for those exchanges, wallets, and merchants to work, there have to be some users who are willing to buy the currency that these miners are now selling. And in order for those users to be buying that currency, they have to be following the same rules. So if miners implemented a change that the rest of the economy in Bitcoin rejected, miners would continue to mine, and they would produce a blockchain with these new rules. But they wouldn't be able to sell the currency on that blockchain because none of the exchanges would accept it, none of the wallets would use it, and no one would buy it because everybody's still operating by a different set of rules. Now, that means, of course, that those who are operating by a different set of rules, exchanges, wallets, users, buyers, merchants, etc., no longer have miners mining their chain, which would definitely slow that chain down, perhaps even stop it for a while. But if that economy still has economic purchasing value, some of the miners might decide that they might want to mine that chain where the rewards have really gone up because there isn't that much competition for mining. Those miners would actually make better profits. So they would defect and start working for the economic majority. And as soon as you immediately see how things balance out pretty quickly. Consensus is a tricky thing to understand. One of the most important is that there are multiple constituencies of consensus. Developers who write the rules but can't force anyone to run them. Miners who mine blocks but can't force anyone to buy the currency or accept those blocks as valid. Wallets that can produce transactions but can't force any miners to mine them or any users to use the wallets. Merchants who sell products but can't force anyone to buy those products or give them the currency they want, et cetera, et cetera. Everybody seems to have power, but they only have power if they play by the majority rules. And if they stop playing by the majority rules, they are the ones who are losing out economically. And so as a result, consensus is something where you can have a lot of power as long as you keep doing what the majority says. The moment you try to go against the majority, that power becomes very, very weak very, very quickly and comes with significant economic costs. That's how consensus stays together. All right, let's quickly check and see how things are going on the chat room. Rule asks, does the Bitcoin network ever go down for maintenance or system upgrade? No, it doesn't. Unlike the banking system, Bitcoin is up 24 hours a day, 7 days a week, 365 days a year. Current uptime for the Bitcoin network is 99.99% and higher. In fact, you can check. There's a nice website that can tell you that. And I'm going to check the URL to make sure it's correct. There we go. Bitcoinuptime.com. Currently functional for 99.99214516.8% of the time since inception, January 3rd, 2009. Where is that missing 1,000th of a percentage point? It's actually probably a disruptive fork that happened in April of 2013 due to a bug in the system that delayed things for about 25 blocks. And again, the system didn't go down. It just slowed down. And then all of the transactions eventually went through, but they were just delayed by 25 blocks. Rule asks, how can a node running on one software, for example, Bitcoin Core, communicate with other nodes running a different software? How does a miner decide which software to use? Is it common for a miner to switch to another software? That's a great question. So there's a difference between the software, the protocol, and the consensus rules. And all three matter. So you can have one piece of software, Bitcoin Core, and that has a certain implementation, but it uses the common protocol to communicate on the network, and it follows the common consensus rules. Now, Bitcoin Core, as the reference client, tends to lead in what the interpretation of the protocol and the consensus rules is, but nobody has to run Bitcoin Core. You can run a different software. For example, there is an implementation in Node.js called bCore, which is fully compatible in the protocol level, fully compatible in the consensus rules. There's another implementation called LibBitcoin, and LibBitcoin is fully compatible with Bitcoin Core in the protocol and in the consensus rules. So by speaking a common language and following the same rules, these three different clients can communicate on the same network, arrive at the same consensus as to what has happened on the network, and continue to remain within consensus by following those rules. A miner can run any one of those, for example, to do mining, and it really depends on what their preference is in terms of scalability and code quality and maintainability and security. Is it common for a miner to switch to another software? Not really. And part of the reason for that is because Bitcoin Core has demonstrated an extremely high level of quality with very, very well tested software that's tested not only by the developers, but of course by everybody else who's running it, and very high standards for code maintenance and security updates, which means that a miner switching to another software, they can, of course, do that. If they believe that the other software will be better maintained, deliver better quality code, or more secure code than the Bitcoin Core project. So far, that doesn't seem to be happening. Most miners use, I think all miners, in fact, use Bitcoin Core because it's proven to be the most reliable software out there. All right, let's see. All right, so Susanna asks, if I'm not running a full node, is there another way to practice commands? Susanna, you can run a fully validating node that doesn't store the entire blockchain to practice RPC commands, which I'm assuming you're talking about RPC commands. RPC commands are the commands that you use to talk on the standardized RPC interface of Bitcoin Core. And so you can also use those with the command line interface command Bitcoin-CLI. If you're not running a full node, there really isn't a way to practice commands unless you find someone who is running a full node who will give you RPC access to it. But honestly, you can run a full node, and you can configure it to not consume too much disk space and bandwidth. It will need to fully sync, and that may take a couple of weeks, but it's worth doing because you only need to do that once. Susanna asks, can you explain the vanity gen command, which is a command for generating vanity addresses. What is a vanity address? A vanity address is one where the address has characters in it that spell something interesting. So for example, I have a vanity address that I use, which starts with 1 Andreas. I have another one that starts with 1 love, which is a bit of a Bob Marley reference. And VanityGen is a program that allows you to generate these addresses. And you're thinking, how can you possibly generate an address that looks like that has special characters in it? I mean, private keys are generated randomly. How can you randomly end up with an address that has these special characters? Well, the simple answer is, what you do is you keep trying. So let's take a vanity address with just 1 character. What does it take for me to find an address that starts with 1A? The 1 is part of the Bitcoin address format. What does it take for me to find an address that starts with A? Well, there are 58 characters in a Bitcoin address, which means that on average, if I generate 58 different private keys in a row, I'm likely to have 1 of those start with A. Simple, right? If I want to get A, I have to generate 58 private keys on average. Maybe it's not going to be 58. Maybe it takes me 60, 70, 80, within a small deviation from that 58. I am going to find a private key that, when converted to a public key and then an address, starts with A. Great. Now, what if I wanted to start with AN for Andreas? I'm going for Andreas. So I wanted to start with AN. How difficult is that? Well, 1 out of 58 keys is going to start with A. 1 out of 58 square keys, because the first 2 characters, is going to start with AN. So now I need to generate, on average, 58 times 58 private keys. And if I do that, eventually I'll generate 1 private key that, when converted to an address, starts with AN. And all I need to do is keep that private key, and I have a vanity address that starts with AN. If I wanted to do this with Andreas, ANDREAS, and I'm counting with my fingers under the table, is 7 characters. And so 7 characters is 58 to the power of 7. Oh boy, that's a lot of addresses I need to generate, which means it's a lot of private keys I need to try. On average, if I generate 58 to the power of 7 distinct private keys, on average, one of them will, just by coincidence, start with 1 Andreas. And that requires a very, very large amount of compute power. VanityGen will do that. You can even set up VanityGen to do it with a GPU. In fact, to generate 1 Andreas took about a week, and it's used about 20 GPUs running in parallel 24 hours a day for a week to generate enough addresses, 58 to the power of 7, to find one that started with 1 Andreas. So that's how vanity addresses work. Modestas asks, since 3 pools control 51% of the network, what other methods could be used to improve the network, as increasing the hash rate seems to give no further benefit? Well, Modestas, increasing the hash rate does give a very significant benefit. And the benefit it does give is that it makes it harder for someone to attack the network, because they have to produce more hash rate than that. And even though it appears that 3 pools control 51% of the network, we don't know how much of the hashing power behind those pools is owned by the same people. People may participate in a pool that has a lot of hashing power because that will give them a better rate of return. It will smooth their returns. Just like if you're playing the lottery, if you join a very big group that's playing the lottery, you're going to get more frequent wins, smaller wins, but more frequent ones that are more predictable. And similarly, if you join a pool that has a lot of the hashing power, then you can get a lot better returns. Now, you may not agree with the politics of this pool, and you certainly don't want them to do a 51% attack. If the pool started misbehaving, if it started trying to use your hash power to do an attack, maybe you'd leave that pool. In fact, we've seen that happen before. At some point, the ghash.io pool had just about 49% of the hash rate. And when that became obvious on the network, participants started abandoning it. So just because a pool seems to control 51% of the hash power, that doesn't mean they actually control that hash power. They're just a point of aggregation. The hash power can be owned by people who may decide not to participate in that pool. Also, attacking the network with 51% is mainly a denial of service attack. You can do some limited double spending, and you can maybe force a change in the consensus rules. But if the economic activity disagrees with that, a 51% attack on the network can only slow down the network and cause disruption temporarily. It costs a lot of money. Instead of doing that, the miners could be mining according to the rules and earning reward that's worth millions of dollars a year, billions of dollars a year. So therefore, why not just mine? And that's exactly how it works, and that's exactly what happens. People don't use a 51% attack because mining, according to the rules, is more profitable. Modestus asks, how do you stop miners from creating empty blocks when they create a regular one? Well, you don't. And in fact, you don't want to. There's no reason to stop miners from creating empty blocks. If a miner creates an empty block, that doesn't reduce the capacity of the network. That's really, really important to understand. If a miner creates an empty block, that doesn't reduce for anybody else the probability of somebody else finding a block immediately afterwards. And so it increases the security of the network for every block mined, regardless of whether it's empty or not. If you have a block that is found now, that doesn't change the probability of finding a block in the next second. These are probabilistically independent events. And so miners creating empty blocks simply forces everyone to restart their calculation, but doesn't change the probability that they will find a block within the next second. In general, you should think of empty blocks as adding to the cumulative proof of work and difficulty of a chain, and therefore increasing its security and increasing its immutability. There's also good reasons why miners create empty blocks. When a miner first receives a winning block from the network, they have to validate it, they have to validate every transaction within that block, and they have to remove those transactions from the mempool and create a new candidate block. It takes a few seconds, maybe just a few hundred milliseconds. But in mining, a few hundred milliseconds is time. And why would you stop mining? You don't stop mining. What miners do is they start mining for an empty candidate block while they're doing the validation. And so if they find one during that time, they'll publish it and then continue to do the validation for a block that has transactions. They can't put transactions inside a block until they have validated all of the previous block's transactions to ensure they're not double spending. Otherwise, they're wasting their mining power. And that's why empty blocks get created. That's one of the reasons why empty blocks get created. Empty blocks are not a bad thing. They're part of the protocol. Check with the chat happening. Susanna asks, if my node finds a block, are those verifications automatic, or does a person need to do some manual work to enable it to go through? No, Susanna, this is entirely automated. There is no manual process whatsoever. The software mines, the software validates, the software verifies, the software propagates. There is no human involved at all. It would be impossible to have a human involved. because of the speeds we're talking about. A delay of milliseconds can cost hundreds of thousands of dollars a day. So absolutely not. No people are involved in this. You, as a person, choose what software to run, and by extension, choose what consensus rules your software will follow, what policies the mining program will follow. But once you've made those choices, you run it, and that's it. All right, I think we've reached the end of our session. Thank you so much for participating. Please remember to study online and put your questions in the forums as early as possible so we can collect all of the questions, prepare them for this live session, and present some good answers. I hope to see you all next week for another session of the massive open online course for the University of Nicosia's master's degree in digital currency. This has been Andreas Antonopoulos answering your questions. Thank you so much again.